Hello and welcome to video lesson 11 on torsion. Our learning objectives for this particular session are to define the polar moment of inertia for a cross section, to calculate shearing stress as a function of radial location for circular and annular cross sections, and to determine angles of twist in circular shafts. For this session, you should read Beer and Johnston section 3.1 and 3.2. So let's talk briefly about polar moment of inertia. So in general, we're going to call it J, and that's equal to Ix plus Iy, which is equal to the integral over the area of x squared plus y squared dA, or what we will call r squared dA. We will only be concerned with circular cross sections because only circular cross sections will not undergo warping when we apply torsion to shafts. Non-circular cross sections will warp, and the solutions that have been developed for circular shafts are not valid for non-circular shafts, and the general results aren't going to hold. However, circular shafts are an extremely important problem, especially for mechanical engineers. So it is important to study this solution first of all, and by understanding what happens to a circular shaft, it becomes a lot easier to understand what happens to a non-circular shaft. To summarize the main results that we have for torsion, for shearing stress in circular sections, we would have the shear stress tau equal to T, which is the torque on the section, times rho, which is the radial location of a point of interest on the cross section, divided by J, which is the polar moment of inertia of the cross section that's being subjected to torsion. And if we follow this, we would see that tau would go to zero as rho goes to zero as we get closer and closer to the center of the shaft. And then the shear stress becomes larger and larger until we get to the very edge of the shaft, which Beer and Johnston calls C for the edge. So tau max equals TC over J. If I wanted to get the shear strain, I could use Hooke's law. So gamma is equal to tau over G. So the shear strain is largest at the very edge, and it goes to zero as the as I approach the center of the shaft. So let's talk briefly about the angle of twist and the shear strain. So if I was to draw two lines on the outside of the shaft and see where these hit the circular edge of the shaft, the angle that these two lines make is what we would call the shear strain. So for the side of the shaft, these two lines make an angle that we would call the shear straft, the shear strain when the shaft is subjected to a torsion T, resulting from the torque T. However, the angle of twist of the shaft would be the angle between these two red lines. And the formula for the angle of twist is phi equals TL over JG. And we could have similarly stepped shafts that are subjected to multiple torques. And we could break up a shaft segment by segment and find the total angle of twist as the summation of TL over JG. Now you might notice that this looks very similar to delta equals PL over AE. So yes, in fact, this is analogous to what we've done before with axially loaded shafts, and all of the same types of problems, the indeterminate problems, could also be solved using methods of superposition. However, we're not going to do that in this course. So as an example of how we would apply the torque the torsion formulas. Let's figure out what the torque T would have to be to result in a maximum shearing stress of 400 megapascals. Now, one handy unit conversion that you may or may not have thought about is 1 centimeter to the fourth is equal to 10 to the negative 8 meters to the fourth. And I wanted to put that out there before I did any arithmetic with J. So for J, the polar moment of inertia, I would have that equal to pi over 2 times the outer radius to the fourth power, which will be 2 centimeters over 2 raised to the fourth power, minus the inner radius, which is 1.5 centimeters over 2 raised to the fourth power. Multiply that by 10 to the eighth, and I would have J in meters to the fourth. That gives me a polar moment of inertia of 1.07 times 10 to the negative 8 meters to the fourth. So if I'm interested in the maximum shear stress, tau max, that's equal to Tc over J. And I can solve that for the torque that would set the max shear stress equal to 400 megapascals. So inverting that equation for T gives me T equal to tau max times J over C. So all I have to do is plug in the correct numbers of 400 times 10 to the sixth newtons per meter squared. That's 400 megapascals times 1.074 times 10 to the negative 8 meters to the fourth. And then C is 0.01 meter. That would be the outer radius. So the torque required to develop the stress of 400 megapascals is 429.6 Newton meters. Now let's determine the angle of twist for the same shaft if it was subjected to a torque of 500 Newton meters and G of 100 gigapascals. And of course, we're going to assume the shaft would not yield under these conditions. So for this particular instance, we need to apply phi is equal to TL over JG, the equation for angle of twist. And in this case, I would have 500 Newton meters times the length of 0.24 meters. Divide that by J, which is 1.074 times 10 to the negative 8 meters to the fourth. And then G is 100 times 10 to the ninth for gigapascals, newtons per meter squared. And when I take a look at all of the units, I would notice that this Newton cancels this Newton. This meters to the fourth is taken care of by this meter, and this meter squared, and I am left with something that is unitless. So whenever I apply this formula, phi is going to come out in radians, not in degrees. It's going to come out in radians. That's all for lesson 11 on torsion.